Hi everybody, welcome to your lesson on climate change. Before we get into climate change, I'd like to review the difference between weather and climate. So weather is constantly changing, and weather refers to the state of the atmosphere at any given time and place. So weather is when you look out the window and say, what's the weather like? And climate is based on observations of weather that have been collected over many years. And those collected observations help to describe a place or region. So climate is when you look out the window many times and you do some data analysis on those observations to get the climate. Climates are classified by the Köppen climate classification system, and it's named after a person, and the system's used to classify the world's climates and is based on two things. The two factors are the annual average temperature and the annual average precipitation. Since water heats and cools slower than land, it takes a long time for the ocean to heat up, and it takes a long time, once the ocean heats up, for it to cool down compared to land. So because of that, locations that are near larger bodies of water are cooler in the summer and warmer in the winter because of the water's influence. And so the Köppen climate classification system, you'll notice that places that are near water have different classifications than places that are on land. So we are moving into resources, and resource use will move us into climate change. So resources, this is review, but I think it's helpful to go over before we jump into climate change. So resources are naturally occurring and considered valuable, any kind of resource, and resources can be either renewable or renewable. They can be replenished over a fairly short period of time, months, years, or even decades. Examples: plants, animals, natural fibers, wind, water, sunlight. Trees can be renewable, but depending on how fast we cut them down and plant and regrow, trees can also be non-renewable. So non-renewable take millions of years to form and be replenished once they are used. So examples of non-renewable are coal, oil, natural gas, metals such as uranium, iron, copper, gold, and sometimes trees. So fossil fuels supply most of our energy, as most of you know, and fossil fuels come from coal, oil, shale, natural gas, and they're called fossil fuels because of how they form. Come from plant and animal remains and take a very long time to form. So this is a great pie graph showing you that 86% of the U.S. energy consumption is from fossil fuels. You can see that petroleum is the largest. The next largest is split between coal and natural gas. And then you've got nuclear power and renewable energy weighing in at 8% and 6%. Renewable only 6%. So problems with fossil fuels, in addition to the fact that they take a really long time to reform and are non-renewable, they also cause acid rain. Acid rain is really harmful to ecosystems, to plants, animals, aquatic life. Fossil fuels, as I just said, they're going to run out in the near future. The rate that we're using them is much faster than the rate that they can be replenished. And fossil fuels cause global warming. So getting into global warming, we've got to first talk about the greenhouse effect. The greenhouse effect is a natural process that warms Earth's lower atmosphere and surface. Nitrogen and oxygen are two gases that make up 99% of the volume of clean, dry air. It's actually 78% nitrogen. So there's a misconception that the air we breathe is oxygen. It's actually mainly nitrogen. So please keep that in mind. The other 1% is water vapor, carbon dioxide, methane, and other gases. The two most important heat-absorbing gases in the lower atmosphere, so where we are water vapor and carbon dioxide. So water vapor and CO2, which is carbon dioxide, they act like a blanket over the Earth. Without our blanket, we would cool to very cold temperatures within hours at nighttime as soon as the sun went down. And so we depend on our natural greenhouse effect to really regulate our temperature. We'd be really hot in the day and we'd be really cold at night if we didn't have this cloud cover and if we didn't have our water vapor CO2 blanket to keep us warm. So greenhouse gases allow incoming radiation from the sun to pass through. So they're transparent, like you can see through them, and absorb Earth's radiation, thus creating heat. However, the rapid growth of industry in the past 200 years has led to the release of larger amounts of greenhouse gases, which means that we have a much bigger blanket. So burning fossil fuels increases the greenhouse effect by releasing more carbon dioxide, CO2, into the atmosphere than the Earth can handle. So it's kind of like when you have too many blankets at night and you get super hot, you want to rip some blankets off because you need to cool off. That's what's happening with the greenhouse effect. There's too much CO2 built up and it's too hot. There's too big of a greenhouse effect for Earth. So here's a great diagram. Solar energy that's coming from the top left comes down, passes through the atmosphere, warms Earth. Some of the sun's energy is reflected back into space, and the greenhouse gases in the atmosphere trap some of the heat. That's normal, natural. We need it to help regulate our temperatures. However, so the left side, normal greenhouse effect. The right side, crazy enhanced greenhouse effect. Too much heat, too thick of a blanket. So now we are moving into global warming. So during the 20th century, Earth's average surface temperature has increased the worst in the past 30 years. Global warming is an increase in the overall temperature caused by human actions. So greenhouse is natural, but humans are making the greenhouse effect enhanced, which is then leading to global warming. I'm actually going back to CFCs for a minute. I'm going to touch base with y'all in the lesson check-in with this, but CFCs also, they also last in the atmosphere for a really long time, and they break apart O3, and we haven't gotten to O3 yet, but O3 is ozone, the ozone that protects us from the sun's harmful rays. So keep that in mind, and in just a couple minutes we'll get down to ozone, and I'll go over how CFCs impact ozone. Okay, so consequences of global warming. So because we'll have hotter temperatures, the melting of polar ice will increase, which means the amount of seawater will increase, and that will erode and flood coastlines. Longer-term changes in climate patterns, which would include more drought as well as more flooding, would also occur. Because we'd have warmer waters, and warmer water is the recipe for strong hurricanes, we would have more hurricanes and tornadoes because of that increase in ocean water and atmospheric temperatures. So the ocean temperatures would be warmer and the atmosphere temperatures would be warmer. Changes in climate means changes in ecosystems and organisms, and harmful bacteria can survive longer. So as the greenhouse effect increases, so does global warming. So in order to do something about global warming, we need to go to the root of the problem and find a way to emit less greenhouse gases. Okay, so air pollution, the largest source is from our transportation. Our transportation, if you remember from a few slides back, mainly our sources of, or all of them right now are, okay, not all of them, but most of them come from fossil fuels. Sulfur and nitrogen oxide are the two main pollutants, and those cause acid rain. These pollutants are added to the atmosphere whenever we burn fossil fuels, coal and others. So, ozone. Ozone's the form of oxygen that combines 3 oxygen atoms. The kind we breathe is 2 oxygen atoms. So it's a molecule, 2 O's stuck together is the one we breathe, and 3 O's combined is the ozone that lives up in the stratosphere, which is the ozone layer, which protects us from the sun's harmful UV radiation. So O3 is good as long as it's up in the stratosphere. O2 is good as long as it's in the troposphere where we breathe. So when you have CFCs, the chlorofluorocarbons, they actually break apart O3 and cause it to become O2. And in the stratosphere, O2 is not a good thing because O2 number one, we aren't living in the stratosphere, so we don't need it to breathe. And number two, we need O3 in the stratosphere because we need it to protect us from the sun's harmful UV radiation. So if the CFCs are breaking apart O3, then that's what's creating the ozone hole. So then we have pollution in the troposphere, O3, which is harmful ozone, which causes an increase in asthma and lots of other harmful effects to humans and plant life and wildlife. So bottom line, CFCs break apart O3 into O2. O2 does not protect us from the sun's harmful rays. We do need it to breathe, but we need it in the troposphere, not the stratosphere. And some of you might remember the saying from middle school, good up high, bad nearby. So O3 is good up high in the stratosphere, but bad nearby in the troposphere. Urban heat islands are urban areas or metropolitan areas that are significantly warmer than the surrounding rural areas because of human activities. And heat islands are worsened by global warming. So a great example is carpool. When we're out at carpool, it's much hotter because of the pavement and concrete than it is when we're out by our gardens where there's trees and grass. So cooling strategies to reduce heat islands can help lower greenhouse emissions that could cause climate change. So this diagram or this chart is really great. It shows you differences in temperature in different types of areas. So we've got rural, suburban residential, commercial, downtown, urban residential, parks, suburban residential again, and rural farmland. So you see obviously the hottest temperatures are in downtowns, hence the name urban heat island, because of the lack of plants and grass and trees. And so you'll find that some of the cooling strategies that are used, specifically in Charlotte, are to have a plan for planting a certain amount of trees to help offset the urban heat island effect from too much building or concrete asphalt materials.